In previous videos, we have studied general uncertainty and probability models for the uncertainty. From this video on, we will study a particular kind of uncertainty, which is random variables. Roughly speaking, a random variable represents the uncertain and numerical outcome of a random experiment. More formally, in order to define a random variable, we need to first have a probability model as P. So this parenthesis as P represents a probability model, where S is the sample space that we discussed before, and P is the probability measure for that sample space. In the context of random variables, the sample space is also called the state space. It represents all the states of the world. And P is the probability measure for the sample space. For discrete sample spaces, SP, the pair, can represent a probability model. Now let's define random variable. A random variable is a function, typically denoted capital X, that assigns values to each point in the sample space, or to each outcome in the sample space. Or in other words, to each state of the world. For each fixed state, the value x of little s is also called a realization of the random variable. It might not appear so intuitive to many of you that a random variable is a function, but you're going to see that this way of thinking about random variable is useful once we consider several examples. The first example we consider is the random variable for hurricane damage. Suppose that a hurricane is moving toward Houston and it's expected to land tomorrow. There are 4 possibilities for the landing of this hurricane, which are represented by 4 states of the world, 4 outcomes in the sample space. M stands for missing, that is, the hurricane lands outside of Houston. And W stands for west, that's it lands on the west side of Houston. And E stands for east, it lands on the east side of the city. And C means it lands heads on, like in the center of the city. Now the probability model that we have for the hurricane is represented in this table. The probability of missing is 5%. Probability that it lands on the west side is 45%. Probability that it lands on the east side is 30%. And probability that it lands in the center of the city is 20%. We use X to denote the numerical outcome of hurricane damage, the uncertain hurricane damage to the city of Houston. Suppose that the damage would be 0 if the hurricane misses the city. The damage would be $4 billion if it lands on the west side, and also $4 billion if it lands on the east side, and $20 billion if it lands in the center of the city. Now you can see the random variable x is a function of the state space of the state of the world. It's a function that maps from the state of the world to the numerical outcomes of the damage. Using the probability model for the state of the world, we can figure out the probability of x equal to each of these values. What is the probability that there is no damage? Probability x equals 0. X equals 0 corresponds to one state, one outcome, that's m. So that equals the probability of the event that equals m. And this is 0.05. What about the probability that the damage is less than or equal to $4 billion? And that corresponds to three states, three outcomes in the sample space, M, W, and E. So that should equal to P of M, W, and E. And now we can add up the probability of these three outcomes. That's 0.05 plus 0.45 plus 0.3. And that is 80%. So there is 80% chance that the hurricane caused less than or equal to $4 billion of damage. Now, we distinguish two kinds of random variables, discrete random variables and continuous random variables. Discrete random variables have a finite or countable number of possible values. Remember what countable means. Countable number of possible values, that means the values can be counted as 1, 2, 3, 4, 5, 6 to infinity. So a random variable is a discrete random variable if it has a finite or countable number of possible values. On the other hand, a continuous random variable does not have a finite or countable number of values. It may take all the values in a continuum. What is a continuum? Let me give you a few examples. A continuum is something like the 0 to 1 interval, or the real line denoted by R, or other intervals on the real line. Let's for now focus on discrete random variables until further notice. We will talk about continuous random variables, but let's start with discrete random variables. The first thing for a random variable is distribution. Distribution of a discrete random variable, it reports the probability of all the outcomes of the random variable, or all the realizations of the random variable. The probability of all the realization of the random variable. For example, for the hurricane that was going to land in Houston, there are three different values for the damage of the hurricane: 0, 4, and $20 billion. The probability for x equals 0 is 0.05. That's the probability of missing. The probability of x equals 4 is the probability of east and west, right, landing on either side of the city, which is 0.45 plus 0.3, which is 0.75. And the rest of the probability is for x equal 20. This distribution that lists all the probabilities, the probability of all the realizations, is also called the probability mass function of X, or PMF of X. Usually the PMF is denoted little f with a subscript capital X and with an argument lowercase x. So the lowercase letters usually stands for the realization, that's the lowercase, and the capital letter X usually stands for the random variable. Sometimes the distribution of the random variable is quite complicated to look at. For example, if the random variable takes many values, then it's useful to have some summary information about the distribution. This kind of summary information is called the traits of random variables. We will study two traits of random variables. The first one is the expected value, also called the expectation of the random variable. What is the expectation of a random variable X? Expectation of the random variable X is often denoted as E parenthesis X. It is the weighted average of all the possible realizations of the random variable. What about the weights? The weights are the PMF values for the realizations. So this is the definition of the expected value. Now consider an example where expected value can help us to make decisions. This example is kind of a little complicated, but it's quite relevant for the present time. Let's spend some time reading the setup. So in epidemics, like the one we are in right now, test and quarantine is considered a very important technique to control the spread of the pathogen. Often it is necessary to test a large number of people in a short amount of time. And this is where batch testing comes in handy. So what is batch testing? In batch testing, the blood sample or nose swab sample or saliva sample, whatever sample that you use to test for the presence of the pathogen, the sample of B individuals are pooled together, and the pooled sample is tested. If one of the individual has the pathogen, then the pooled sample also has the pathogen, and the pooled sample will be tested positive. Let's for now ignore the accuracy issue of the test. Let's say the test is 100% accurate. So if at least the one individual has the pathogen, the pooled sample also has the pathogen. So the sample will be tested positive. If none of the individual has the pathogen, then the pooled sample also does not have the pathogen, and the pooled sample will be tested negative. So when we have a negative test for the pooled sample, we know that implies all the individuals in the batch are negative for the pathogen. Then we don't have to do any more tests. So one test will tell us all B individuals do not have the pathogen. But then if the pooled sample is tested positive, we need we need to do more testing. We need to test the individuals one by one to figure out which of them have the pathogen. Now, that is batch testing. Okay? The batch testing is done in this way. Now, what we are interested in is a random variable x that stands for the number of tests needed per person in the batch testing. The number of tests needed per person now is random. It depends on whether the pooled sample is tested positive or tested negative. When the pooled sample is tested negative, that means the pooled sample has no pathogen. That implies none of the individual in the batch has the pathogen. That means the pooled sample test is the only test we need to do. So in that case, we only need one test for all B individuals, or 1/B test per individual. Now, if the pooled sample test returns a positive result, that means the pooled sample has the pathogen and at least one of the B individuals has the pathogen. We then need to do the B individual tests one by one to find exactly which one has the pathogen or which ones have the pathogen. In that case, the number of tests needed to be done per person will be B plus 1 divided by B. So there are two possible values for the realization of the random variable x, 1/B or B plus 1/B. What about the PMF for the random variable? What's the probability that the pooled sample has no pathogen? We need an extra information. We need to suppose that the positive rate in the population is something, let's say 1%. That is, for each individual, the probability that the individual has the pathogen is 1%. And the individuals are independent from each other. So the probability that all B individuals are negative equals the probability of each individual being negative raised to the power B. And conversely, the probability that x equals B plus 1/B is 1 minus 0.99 to the power B. So the PMF is given by this. Now we can calculate the expected value of x, expected number of tests needed per person. That should be 0.99 to the power B times 1/B plus 1 minus 0.99 to the power B times B plus 1/B. This is something that you can calculate for each B, which, remember, is the size of the batch. Let me give you some examples. If B is 2, let's you put 2 people in each batch. E of x is around 0.51. And when B equals 10, E of x is around 0.2. That's if you use a batch testing with 10 as the batch size, then you only need about 0.2 number of tests per person. Or in other words, to test 100,000 people need only roughly 20,000 tests if we put 10 people in each batch. So this is where expectation calculation can help you to save costs or save time for conducting a large number of tests in an epidemic. The next trait of random variable is variance. We not only care about the expectation or the average value of a random variable, we also care about the dispersion of the random variable. The variance of a random variable x is defined to be the expectation of the square of the deviation of x from its expectation. If the random variable doesn't have much dispersion, then it's always around its expectation, then this deviation will be close to zero, variance will be small. But if the random variable is different from its expectation a lot of the time and differ from the expectation a lot, then the variance will be large. So the variance measures the dispersion of the outcomes of the random variable. In terms of PMF, this can also be written as a weighted average of the deviation from the expectation, standard deviation. Standard deviation is another way to measure the dispersion of the outcomes. Standard deviation is defined to be the square root of the variance. But you might wonder, now that we already have a measure of dispersion, that's the variance, why do we give the square root of the variance a different name? But the reason is that the variance of x is an average of something squared, the deviation of x from expectation squared. So the variance of x is not on the same scale as x. It doesn't have the same unit as x. Once we take the square root, we get back the original scale of the random variable. Say if the random variable is in terms of dollar, then standard deviation can also have the same unit. So that's why we give a square root of the variance a different name. Often we use the Greek letter sigma x squared to denote the variance, and we use sigma x to denote the standard deviation. Now let's consider an example. In a car dealership, they are planning to sell two new car models, Xenon and YOLO, where Xenon is a sedan and YOLO is an SUV. Xenon has a better gas mileage and YOLO has a worse gas mileage. It burns more gas. YOLO burns more gas per mile. Depending on the gas price, the sales of the new cars may be different. Suppose for the next year, we expect the gas price to have the low gas price state, the medium, and the high gas price states. Suppose the probability that the gas price will be low is 0.3, and the probability that it's medium is 0.4, probability of high is also 0.3. In a low state, the sales of xenon will be lower because xenon saves gas, but it's a smaller car. In the medium case, it's a little higher, and in the high gas price case, people are more sensitive to gas mileage. They will buy more of the gas-saving car. And it's the opposite for YOLO. We can calculate the expected value of X and the expected value of Y. Expected value of X is 0.3 times 100 plus 0.4 times 120 plus 0.3 times 140, which equals 30 plus 48 plus 42, which is 120. So 120 xenons are expected to be sold next year. We do the same thing for YOLO. EY equals 0.3 times 180 plus 0.4 times 120 plus 0.3 times 60, and that turns out to be also 120. So the two car models will be expected to sell the same number. Their expected sales will be the same. However, just by looking at this distribution, their dispersion does not seem to be the same. Y has more dispersion and X has less dispersion because 100 and 140 are less different from 120 than 180 and 60. Now let's do the exact calculation to see how different their variances are. Now recall that the expectation of X and Y are the same. The variance of X will be 0.3 times 100 minus 120 squared plus 0.4 times 120 minus 120 squared plus 0.3 times 140 minus 120 squared. And this is 0.3 times 400, and this is also 0.3 times 400, and this is 0. Therefore, this variance should be 0.6 times 400, which is 240. What about the variance of Y? The variance of Y will be 0.3 times 180 minus 120 squared plus 0.4 times 120 minus 120 squared plus 0.3 times 60 minus 120 squared. And we look at this expression, we find that this is 0.3 times 60 squared. This is also 0.3 times 60 squared, and this is 0. Therefore, the variance of Y is 0.6. times 60 squared, which is 3,600. 0.6 times 3,600 turns out to be 2160. So the variance of y is a lot higher than the variance of x. So the sales of YOLO is a lot more dispersed than the sales of Xenon. The last topic of this video is functions of random variables. Usually when we study random variables, we often have some basic probability model, basic random variables, and we consider functions of these basic random variables. That is a very useful tool to generate a lot of new random variables from old ones. So a new random variable can be generated from old. Let's say the old random variable is x and the new random variable is y. Y might be a function of x. So g is a function. We can also derive the distribution of y from the distribution of x. So the PMF of y at a realization little y equals the probability that big Y equals little y, but we can write that in terms of x. So that is the set of x such that g of little x equals little y. Remember, we are considering discrete random variables, so this is a discrete set of realizations for x. We can sum them up. We can sum up the probability for each of these realizations of x using the distribution of x. So this is how we figure out the new distribution from the old distribution. Sometimes we don't need to figure out the whole distribution of the new random variable. Sometimes we just need to calculate the traits of the new random variable. For example, the expectation. In that case, we don't need to first get the new distribution. Instead, we only need to use the old distribution. So E of y written in terms of the old distribution is this. Is the average, weighted average of g of little x, where the weights are the PMF of the old random variable x. Let's consider an example. In this example, a person called David is buying medical insurance for next year, something that every one of us has to do. He thinks that he's in good health and his no insurance medical cost has the following distribution. So this distribution. He thinks that there are 3 states of the world. The first state is no doctor's visit. He doesn't need to visit the doctors, in which case the medical cost would be 0. He needs to pay nothing even if he doesn't have insurance. In the second state, he might have some mild illness and he visits the doctor, and that might cost $500 without an insurance. And lastly, there is a small chance that he might get severely ill and be admitted to the hospital, and that could cost him a lot of money without insurance, $50,000. And let's say the probability of each state is given by this: 0.8 for no doctor visit, 0.19 for mild illness, and 1% for the severe illness. Now, the old random variable we're considering is the no insurance medical cost, which is 0 in the N status, 500 in the M status, and 50,000 in the severe status. Buying an insurance will change his out-of-pocket medical cost. Suppose he's considering an insurance policy that costs $100 for the year, but the insurance policy also has a deductible of $500. That is, for the first $500 of medical cost, he needs to pay out of pocket. Over that amount, the insurance company will pay. Now, with the policy, his out-of-pocket medical cost is Y, and Y is given by Y is a function of X. Out-of-pocket cost include the insurance policy cost, 100, which he has to pay in any of the state, plus the minimum of the no insurance medical cost and the deductible. If he spends less than the deductible, he pays that amount, and if he spends more than the deductible, then he only pays the deductible. So Y is this function of X. And we can actually figure out the values of Y for each X value. When X equals 0, he pays 100. When X equals 500, he pays 600. And when X is 50,000, he continues paying 600. We can figure out the PMF of Y using this table. There are two possible values for Y, 100 and 600. So the PMF of Y has 2 points, P. So Fy 100, which is probability that Y equals 100. That's also the probability that X equals 0. And that's 0.8. And Fy 600 is probability that Y equals 600. That's the probability that X is greater than 500. That's 0.2. These two numbers give us the PMF of Y. We can calculate the expectation of Y using the PMF of Y. So that's 0.8 times 100 plus 0.2 times 600. And that's 80 plus 120. That's $200 is the expected out-of-pocket cost if he buys the insurance. We could also calculate the same expectation without using the PMF of Y, but using the PMF of X instead. X has three values, 0, 500, and 50,000. And each has probability 0.8, 0.19, and 0.01. So we can calculate it using the PMF of X. That's 0.8 times the value of Y when X equals 0. Remember, that is 100 plus the minimum of 500 and 0. plus 0.19 times 100 plus the minimum of 500 and 500 plus 0.01 times 100 plus the minimum of 500 and 50,000. That you can calculate to be the same as what we get here, also 200.